It is generally believed that Polaris remains fixed in the same position in the sky. However, like all the stars around it, it completes one rotation per day. This rotation is so small in diameter, however, that it cannot be perceived with the naked eye. The North Star is located at 89.37 degrees north latitude. This becomes clear when viewed in stellarium. Let's look south. There, too, the stars follow circular paths. Unlike in the north, where everything rotates counterclockwise due to perspective, in the south it's the other way around. That is clockwise. Stellarium also displays the coordinates of a celestial body and marks it with a... The zenith coordinates are given slightly differently than usual. Our AJ 2000 represents the longitude as a right ascension angle. Here, the vernal equinox Aries serves as the reference point. The right ascension time is added to the hour angle of Aries. You'll see two slightly different values. First, our AJ 2000, which refers to the beginning of the current astronomical epoch on the first day of the year 2000, at 12 o'clock Universal Time Coordinated. Second, calculated based on the current date, since the vernal equinox continuously shifts relative to the stars. After that, the latitude is given as the declination in degrees, minutes, and seconds. You'll also find a transit time. This is also important since the celestial body will then be exactly due south, or due north if your location is south of the object's orbit. The transit time is therefore given only once, even though the object appears to be back in the south, just above the horizon, 12 hours later. Aries is the central reference point of the starry sky. The seasons are defined by the sun's position relative to Aries. This is important. To illustrate this, let's take a quick look at the time and date and at one of my tables. On June 26th, summer began at 8:24 Universal Time Coordinated. The sun above the Tropic of Cancer formed a 90-degree angle with the vernal equinox, which is shown as a blue line in the table. The start of fall is on September 23rd at 0:05 Universal Time Coordinated. The sun at the equator forms a straight line with Aries across the North Pole. December 21st. The start of winter at 8:50 UTC. As with the start of fall, the angle is again 90 degrees. The beginning of spring on March 20th at 8:24 p.m. Now the sun is exactly on Aries and the equator. Let's get back to what causes the circular southern star trails that we saw in stellarium. I chose Cape Town, South Africa, as the location. The constellation Octans forms a relatively small triangle with its 3 stars. Beta Octantis has a right ascension of 22 hours, 48 minutes, and crosses the meridian at 1:55 Universal Time Coordinated. Delta Octantis has a right ascension of 17 hours, 35 minutes. Transit at 17:35. New York Octantis, right ascension of 21 hours, 44 minutes, and transit at 0:47. Here, the orbital paths of the 3 stars are marked in different colors. New York Octantis has the northernmost orbital path at 77.26 degrees south, and Delta Octantis has the southernmost path at 83.79 degrees south. On the map of the flat Earth, it's reversed. Delta Octantis has the southernmost path of the 3. Thus, the greater the actual circumference of the Earth, the narrower the visible circular path of the southern stars in the sky becomes. The supposed southern celestial pole, Sigma Octantis, also known as Polaris Australis, is also just a star that, like all stars, orbits the North Star in a clockwise direction. It lies 88.84 degrees south, so it's even slightly farther south than Delta Octantis, and that makes its orbit in the sky even tighter. We'll take a closer look at this rotation around the North Star in another table. Using this table, you can calculate all 88 of the international constellations. The 88 constellations consist of a total of 3,690 stars, which can be identified by their HD numbers. But only the brightest and most prominent stars form the actual constellation. The octant triangle and the current position of the supposed southern celestial pole, marked as a red dot at the edge of the map. This allows you to compare the times of the stars' transits in stellarium. Beta Octantis crosses the Cape Town meridian at 1:55 at 18.6 degrees east longitude. This corresponds to 341.4 degrees in hour angle from Greenwich. The dashed line marks the meridian on the map. Using the table, you arrive at the same value. Delta Octantis in stellarium, and in the table at 1735 UTC. New York Octantis, 047 UTC. Sigma Octantis. Stellarium shows 035, and calculated as 033 and 33 seconds. I'd like to use this table to quickly demonstrate the significance of right ascension. At the beginning of the current astronomical epoch, the vernal equinox was located at 280.46 degrees relative to the Greenwich hour angle. To illustrate this, I'll set the meridian line to this value. It is now located below the blue Aries line because the visual display uses stacked diagrams. Sigma Octantis has a right ascension of 21 hours, 8 minutes, and 46 seconds. If you adjust the time in the table, the star reaches the previously set meridian, and thus the point where Aries was previously located. This is what the individual constellations look like. Near the center of the flat Earth, the individual stars are usually relatively close together. Toward the south, the constellations extend quite far in some cases, as we have already seen with octants. On the left side of the table, the stars of the selected constellation are listed by name and HD number. The fact that these widely spread out constellations nevertheless appear so compact in the night sky can only be attributed to the firmament and the atmosphere enclosed within it, which are responsible for this sophisticated and ingenious play of light. Just as sunlight reaches us from different distances at various times of the year, this effect can also be observed with stars orbiting outside the southernmost path of the sun. I think that the light from these stars is transmitted by the firmament and then converges in a southerly direction, regardless of the observer's location. The constantly changing range of sunlight can also be demonstrated. The sundial table calculates the times of sunrise, the sun's passage through the meridian, and sunset. The times match those provided by time and date. Depending on the location and season, the distance from the sun's zenith to the observer's location changes significantly. The triangle on the map marks the zenith at sunrise, the point of meridian passage, and sunset. The diagram also shows the sun's path, and the small, round diagram indicates the direction toward the sun. Here, the directions sometimes diverge quite widely. A pointer in this compass diagram indicates the geometric direction, which can be easily calculated. The second pointer calculates the perceived direction toward the sun, including atmospheric refraction, and not just for elevation, but also for azimuth, that is, the compass direction, and the results yield the same angles as those from time and date. This calculation comes from an official source. NOAA, the National Oceanic and Atmospheric Administration of the United States, offers the table for download on its website. The original table contains several diagrams showing the sun's path. However, everything is arranged in a somewhat confusing manner. So I removed the diagrams and integrated the table onto a separate sheet. I invite you to test the table and draw your own conclusions from it. For me, the difference in distance to the sun in summer and winter confirms the atmosphere's influence on the range of light. Just like with the stars,